Mm, okay.
Ben, did you receive an email? Not Gess, Goldys, please.
Email from you.
Yeah, from Zoom.
Invitation to
The coffee break.
yes, I've got it. No
yeah,
problem.
so you are a co-host of this
yeah.
one.
Yes, I have button start meeting. So
yeah, not yet. after this talk. Yeah.
Okay, I think we can start now. So this is my pleasure to announce a talk by Ben Gess from Bielefeld University. Ben works in strongly nonlinear stochastic PDEs in porous medium, in particular on stochastic porous medium equation, and also on stochastic P-Laplace equations and many others. And today's talk is about large deviations for stochastic PDE. So please, Ben, start.
Yeah, thank you very much, Ben, for the nice introduction. Thanks a lot to all the organizers of this seminar to inviting me for this talk. So it's a pleasure to be here and speak in this context. And yeah, thanks to you guys for showing up. So yeah, today I'm reporting on work with this joint with Ben Fairman and also with Nicholas Diaz. So this is the the closest stuff to what I'm going to show you today. So everything here is based on much more work leading up to this. So there are a list of co-authors that you will see in the end. But yeah, so if you want more details on what I'm going to show today, then you can find it in these two preprints, which are online on Archive. And yeah, given down there. So they're also hyperlinked after the talk. You can have a look. Right, so now what I would like to do today is actually to spend quite a bit of time on explaining the modeling aspects of this work. So in this first part, I spend a lot of time on motivating why these conservative stochastic PDEs that we are considering appear, and also how the stochastic fluctuation should look like precisely. And yeah, this would also serve as a motivation to understand why, in particular, questions of rare events are important in understanding in this class of stochastic conservative PDEs. And then, well, actually, if time allows, so I've certainly too much material here, but if time allows, then I will speak about the more mathematical aspects in how to prove a large deviation principle for this class of stochastic PDEs, which ultimately leads to questions on PDEs with irregular coefficients. So in section 2, actually, everything boils down to questions in PDE theory and well-posedness and stability of solutions to nonlinear PDEs with irregular coefficients. Right, and as I said, so I don't expect to be able to give all the details that I do have on my slides in this talk, but the slides will be made available afterwards. So yeah, I still decided to put it on there because then you can have an extended version just by following up on the slides. Okay, so let's start with the first part, and this will consist on motivating how nonlinear stochastic PDEs appear in non-equilibrium statistical mechanics. So in order to understand this, I will focus on a particular example of a microscopic process and explain the principal setup of how they are connected to nonlinear SPDEs in terms of this model example. But you should really understand this as just one particular example that we choose, which we do also for mathematical simplicity. Okay, so this will be the so-called zero range process. And I already indicate there that we could make other choices. So it would be possible to choose some process like simple exclusion processes or independent particles. This would all be possible. So this is for the sake of the presentation that I consider the zero range process. Okay, and so I've depicted this here. So we look at the process in the finite torus of size n. So we have capital N boxes depicted here. And in each of these boxes, there's a number of particles. So we don't distinguish in between each individual particle, we just care about the total number. So this is typically done in statistical mechanics. You wouldn't count or identify each single atom, but you would just count how many there are at a specific point in space-time, for example. Right, so this tells us that the state space of our discrete process is just the set of maps mapping the torus of a size n to a natural number, which can also be 0. And this will specify the configuration of our particle system. Okay, saying that each container K contains eta of K particles. Right, so this is completely describing the configurations, and now we want to have dynamics on these states. So these particles we imagine to hop around to left or to right with a certain rate. And this is the first thing we have to specify, the so-called local jump rate function G, which is a function of the number of particles in a given site. Yeah, the number of particles, and gives us a rate at which these particles decide to jump. So yeah, if you think about it, if there are n particles in a box, then each of them has a probability to jump. So this function G should always be non-decreasing in the particle number. If you just choose G to be linear, then this would correspond to the particles actually behaving independently from one another. So it's just that you have more particles, the incentive to each of them will jump, so the probability to observe one jump is higher. But there's more you can model with this local jump rate function. So for example, it can increase stronger than linearly, which would mean that whenever you have a concentration effect, like there are more particles in some box, then the jump rate actually increases more than linearly. And this means that yeah, crowding of particles in boxes is avoided because this incentive to jump away then becomes higher and higher. And here already on the discrete level, you see that you would expect that the diffusive effect one can see after rescaling the system, it should actually become depending on this local jump rate function. And you would also expect that if, for example, you choose it super linearly, then you see an increased diffusion, which looks like a nonlinear diffusion equation. And we'll see indeed that this is the case later. Okay, but for now, let's stick to the discrete process. So we have specified the jump rate at which particles decide to jump away. And now we have to specify where they jump to. Again, this is a probabilistically chosen point. So we have a probability kernel P, which gives us a probability to jump from box K to box L. And there are some assumptions flying around. So for example, it's translation invariant. It might be asymmetric, but it has to be centered in this way that the expectation is 0, which means that there's no tendency to jump on average to the right or on average to the left, but on average actually we stay stuck, which is an important assumption because this means that in the end we see diffusive behavior rather than transport behavior. Okay, and with these ingredients we can construct a Markov jump process. This is in a standard way. You write down the generator with these objects, and then you see that you get a discrete process. So this is a process which lives on continuous times, and then at random instances in time, jumps of particles are induced. And then eta will be the corresponding process. So it takes two variables. We have k, the number of the box that we look at, and time t. So then eta is the number of particles in box k at time t. Okay, and all of this is like a toy model for statistical mechanics, where you would be interested in actually looking at a large number of atoms. So capital N should be imagined to be very large, and one would like to understand some kind of average behavior produced by the interaction of these large number of atoms. Of course, there the initial point is deterministic, and here we introduce probability, which can be justified in some cases, and on other settings you have to say that this is the part of the toy model, because the stochasticity makes it easier to understand the invariant measures of this discrete process. Right, so now we don't want to focus on this microscopic picture where we do see the individual atoms, but we want to understand what happens when we look at the system from far away, let's say. So when we rescale space to sort of zoom out, and we speed up the dynamics so that we look at time scales which are very fast, or actually, which are slow in the discrete system, and then we speed them up. So we only see slow time scales. Fast time scales are actually already averaged out, in which we will see. And right, so this is just saying in words that we want to take a hydrodynamic limit, meaning that instead of looking at the discrete discrete space picture on the left-hand side, where we do see the atoms, we want to see a slow evolution over the local densities of atoms. So what you should have in mind is that we have a huge box. So we have a million or more particles, and then this box is made, so capital N is very big, and then we divide this box into smaller boxes. And here in this picture is just one smaller box. And in these smaller boxes, we have an average number of particles. So this average number of particles is associated to one point in this graph. So one point here corresponds to one average density in a small box, whereas the full size would correspond to the large box. Okay. And yeah, the hope is to be able to say, okay, we forget about many aspects of the microscopic dynamics, which are the interesting system that we want to describe. But while taking this hydrodynamic limit, we still retain some non-trivial information, which are, however, easier to describe. So this taking a hydrodynamic limit means to lose information, but to gain a more a model which is easier to describe and to handle rigorously. Okay, so how do we do this now on the mathematical level? So the first thing we do is to encapture this left-hand side picture in terms of a mathematical object, which I call the empirical density field mu n. So you see that mu n, what it does is it puts a Dirac mass, so a measure, on each of the boxes, k divided by n. So now we number the boxes not from 1 to n, but from 1 over n to 1. So meaning that we rescale our system in space, so that even when n becomes large, these measures always live on the interval 0 to 1. right, or on the torus, because we always look at periodic boundary conditions, so that if you hop off the grid to the right, then you reappear on the left. So this guy, after rescaling, these are measures on the unit interval. And then on each of these Dirac masses, we put a factor, which is just the number of particles in this box K at time t, but times n squared. So also here we rescale in time. I mentioned that in words before. You should think of n being extremely large, meaning that here we look at very large time scales, at very large times. Right, and then we have a rescaling factor 1 over n. So this is the empirical density field, and then the hydrodynamic limit means that we look at the limit of this random measure mu n. So remember that mu n is defined by superposing Dirac masses. So these are measures already. And then these are random coefficients. So this becomes a random measure. And the hydrodynamic limit means that we can show that when n goes to infinity, there is a limit to these random measures. And now the point is that in some kind of weak convergence, we have that mu n converges to some limiting object. And while the left-hand side is something which is stochastic, on the right-hand side, we have something which is deterministic. Okay, and you see already the link to large numbers. You start with a random effect, which carries some kind of independence. And then when you repeat this effect for often enough, in the limit, you will see an average behavior. And this is the role of rho bar. And now the interesting thing to observe is that the way rho bar is described is as a solution to a nonlinear diffusive equation. So we have that the rho bar just satisfies a PDE of this type, and because phi can be nonlinear, this makes it a nonlinear PDE. And already here, well, everything is described in terms of the microscopic model. So in particular, this nonlinearity phi can be obtained by averaging the local jump rate over the invariant measures fixed at density rho. So yeah, maybe the right-hand side is too complicated to appreciate immediately if you're not familiar with this theory. But the point I want to make here is that this function phi can just be extracted from the microscopic dynamics. And one can plug in certain particular examples, like if you have independent particles, then you get sort of, in a sense, a trivial limit. So then you get just the heat diffusion here. Phi would be the identity. But if you do something like have a mean local jump rate, which increases more than linearly, you would see a diffusion here, which becomes stronger when you have larger densities rho bar. So this would be avoiding the concentration of mass more strongly. Right, so this is known. And now one can take a step back and look at this again from the application point of view. So still, the object of interest that we want to describe eventually is mu n. And so this is the honest particle dynamics. And now we have found an approximation, rho bar, which describes the mean behavior of mu n for very large particle numbers n. So yeah, there are some questions one may ask after one has derived this hydrodynamic limit. The first one, which is sort of obvious, is, well, okay, we have some kind of convergence, but actually how quick is this convergence? Is this super slow? Then actually the limiting dynamics, it's not really so meaningful, because n, whilst it will be very large, it will be finite. So we're interested in this guy for large but finite n. So if convergence is too slow, then this has not so much to do with the actual system. So we want to understand the speed of this convergence. And the second question, or observation you can make, is that, well, the limiting system rho bar, it can only carry information about the average behavior. So while on the left-hand side we have something which is probabilistic, a probabilistic object, on the right-hand side we just carry over information over its mean. So all the information about fluctuations and random behavior of this distribution on the left-hand side is left, and therefore one might be tempted to get your hands on describing these fluctuations for large n as well. Okay, also this, in principle, it's a standard setup in probability theory. So this would amount to saying that we would like to understand the central limit fluctuation theorem about these nonlinear dynamics. And this is precisely what I'm writing down now. So again, this goes back to these authors. So instead of looking at the empirical density field as on the last slide, we look at the so-called fluctuation density field, Yn. So you see it has a similar form. So we again put a Dirac mass on each box. Here we have the particle number. This is just the same as on the last slide. But now instead of looking just at the particle number, actually we look at the particle number corrected via its mean. So we subtract the mean number of particles in the box. And then we rescale by 1/√n. Like also this already looks like what you would do in a central limit theorem. And actually we can even write it more intuitively. So there's just this equality that the first part is the empirical density field, and then we have subtract the average value of the empirical density field. So that by now we would know that in some weak sense, actually the stuff in this bracket, it should go to 0. So we have to scale it up in order to see something non-trivial. This explains this factor √n, which explodes. Okay, and now we'd like to understand again if there's a limit of Yn and if this limit is non-trivial. Okay, and this has been understood. So, right, indeed, in this setting of the zero range process, one can show that the law of Yn converges weakly in some sense again against the law of some random variable. So now the right-hand side is not deterministic, but stochastic. And since we're looking at the central limit theorem situation, what you would naively expect is that the right-hand side should be a Gaussian. Right, so now it should be a Gaussian in a higher dimensional space, but still be a Gaussian function. And this corresponds to saying that Y should be the solution to a linear stochastic partial differential equation. Right, so and this linearity meaning that since you plug in something which is Gaussian, also the solution will be Gaussian. Right, and this is indeed the case. So also this fluctuation behavior in the sense of a central limit theorem has been solved. And one can see that Y is the solution to this equation, which is a linearized version of the nonlinear diffusive equation on the last slide. So, right, so we have this first operator here, which maybe looks complicated, but what you have to see is that the rho bar is just the solution to the deterministic Pde we had on the last slide. So you first have to solve the deterministic Pde, then you are given rho bar just as a fixed solution. So this factor just becomes a coefficient, right? Which makes this operator look just like a diffusion, a linear diffusion in terms of an operator on Y. And then we have a noise term, and this noise term has a clear and specific form. Namely, it's the divergence of the square root of the nonlinearity, again fixed at the deterministic solution. So again, this is just a coefficient against space-time white noise. So you can already see, okay, this is quite an irregular object because you take the derivative of space-time white noise, but on this level it doesn't hurt us because, well, this is a linear SPDE. So you can just work on spaces of distributions. You don't have to specify nonlinear functions of distributions, so you are safe in solving this. And we can see that, okay, this has a generic form, and having this type of divergence noise is relevant here because it means that in particular the total mass of Y, so the integral in space of Y, is preserved, which corresponds to preserving total density, or total mass of the process, which is built into the zero range process. So there was no dying or creation of particles, they were just hopping around. So we do have this conservation of mass inside of the microscopic system, so it has to be present also on this level of the continuum description and the central limit fluctuations. Okay, so yeah, so here we see these kind of central limit theorems. So now how does this connect to what I indicated on the last slide, that we would like to have a better understanding of the rate of convergence of the microscopic system to to the hydrodynamic limit. And this we can read off now just from the definition of yn. So the point is that here we see mu n and its difference to its mean. So we expect that this guy goes to 0. And now we see that even if we scale it up by square root n, then the limit is something which is non-trivial but finite, meaning that this difference has to decay at least like the square root of n. So this is why I write down in a very informal way that in some sense of a distance, the distance of the deterministic, the stochastic discrete system mu n has to converge to the mean behavior like n to the minus negative 1/2. So n to the minus 1/2. So this is the rate of convergence, and this has to be exact because the limit is not trivial. You see something here which is a law of some random variable. Okay, so now this puts us in a perspective to ask if we can do better, right? So we have this approximative system rho bar, which only describes the mean behavior of the system, and then we see that at best it can describe mu n with an error that scales like this. And yeah, my next point is that actually writing down the central limit theorem also indicates how we could write down an improved model for the limiting continuum object. So this continuum object being described not on a discrete torus anymore, but on the full interval 0 to 1. And yeah, so let's go there. So we can reinterpret star, which was just the setup of the central limit theorem, as a fluctuation correction to our continuum model. So yeah, the first line is just rewriting the definition of yn. So remember, yn was just given as the taking square root n times the difference of these two guys. So I just rewrote this in such a way so that it becomes an expression of mu n. So now this, again, the left-hand side of the system we're interested in, we want to describe by a continuum object. And now we see that this is actually composed of two things, namely its mean and its fluctuation. And we know that the mean will approximatively look like the hydrodynamic limit. So I just add and subtract the hydrodynamic limit here in this next line in order to see that the error we have here is just the error that we see in between the hydrodynamic limit and already the average behavior of mu n. And this behaves better than looking at mu n without the average subtracted from the hydrodynamic limit. Namely, and in this particular case, you can see that at least this decays like n to the minus 1. Which means that our actual system mu n looks like the hydrodynamic limit plus the fluctuation path plus some error which decays quicker than n to the minus 1/2, namely like n to the minus 1. Okay, so this means that I can interpret this this sum of mean plus fluctuation to be a better approximation to our real physical system. So I can set rho n to look like this. So it will approximately look like a deterministic function plus a Gaussian. And we can see that then the error we make, it should behave like n to the minus 1. So this I call a linearly corrected continuum model rho n. And okay, this is a bit imprecise now. So this should be the superposition of the mean plus the Gaussian part. So where we already go to the limit n here. And then we can see that this guy still solves a continuum model, which is looks similar to the one we had on the last slide, namely it's a linear equation in rho n. So again, we have this linearized diffusion operator, and now we have a noise which comes with a small amplitude, 1 over n, but it's the same structure of the noise. Okay, and it has to be this way because we know that rho n it has to converge to the deterministic object. So the fluctuation path has to go to 0 when n goes to infinity, which is reflected by having this small factor in front of them. Right, so this admittedly on a very informal level tells us that we can come up with improved continuum models that not only describe the mean behavior of particles, but which also incorporate information on the fluctuations of this system. So the first benefit is that we don't lose all the informations of fluctuations, and one way to make this clear or beneficial is to see that when we allow these fluctuation components, we can increase the order of convergence that we see as a function of the total particle number. Right. So what are limitations of this linearly corrected model? And yeah, this is the next point. So then we can ask now, since we have a fluctuating continuum model, rho n bar, does it also incorporate the correct information about the microscopic system in terms of rare events? So rare events meaning that we want to estimate the probability that our system rho n bar looks like a given function, rho. So now rho is just some function that we are given, which doesn't have to coincide with the mean behavior. So it doesn't have to coincide with the hydrodynamic limit. So the probability of this happening can actually be very small, right? We know that this guy converges to its mean. So if this deviates from the hydrodynamic limit, then the probability has to go to 0. And now rare events means that we're not content with saying that this probability goes to 0, but we want to understand how quickly this happens. And right, then a large deviation principle or a rare event estimate comes of the form that we say that for large n, this probability behaves like the exponential of minus n. And with a rate, I, which is now depending on the fluctuation that we're interested in. So in this sense, we aim to classify on an exponential scale how quickly the probability of rare events decays. And now if we just start with our model rho n, the linearly corrected continuum model, then we can see that the corresponding rate function has to take this variational form. So it will have to be given as the infimum over all energies G, just given by the A2 norm, where G, the control, has to be chosen so that the fluctuation rho that we want to produce or to see comes as the solution to a linear partial differential equation. So this is a typical form of how we see large deviations or rare events appear in terms of a variational description of the associated rate function. And you already see that this is then coming down to understand partial differential equations as they appear here in the rate function. And okay, for now, let's just take it for granted. This will be the rate function. I'll explain later a little bit why it takes this form. And this would be then how rare events appear in the linearly corrected continuum model. And now the problem is that this is false in the sense that when we look at the true rare event behavior of the particle process mu n, then this also has a large deviation principle, but with a rate function which is different from the one that I wrote down here. So this is the content of the next slide. So yeah, let's start off with actually looking at the true rare events of the microscopic system. Write it down in the same informal way. And again, it's specified by specifying the rate function. The rate function again takes a variational form. So the first part looks the same. We take the infimum over the energies of all controls G. But now G act in a different way, namely they control a nonlinear Pde. So the true skeleton equation, so the skeleton equation always is the PDE which appears in the description of a large deviation principle. It is a nonlinear diffusive equation with a nonlinear hyperbolic part which looks like roughly like the stochastic Pde, but not as evaluated at the deterministic hydrodynamic limit rho bar, but really as evaluated at the solution itself. So this looks like a conservation law part, speaking more from a Pde perspective, where G, the control, is an irregular function. It's just L2. It doesn't carry any BV estimate or anything like that. So this nonlinear PDE actually appears to be a hard to study object. And here I'm already indicating how now challenging questions in nonlinear PDE theory appear in understanding rare events and large deviations in these microscopic systems. Right, and the point I want to make on this slide is that, well, this plainly does not coincide with the rate function that we get from the linearly corrected model rho n bar. Right, I'm just repeating that the linearly corrected model had this rate function, and we see the difference is in the so-called skeleton equation, because the linearly corrected guy, it sees a linear equation. Now, this may be not so surprising because we just did a linear correction, and this corresponds to expanding the nonlinearities and then a sort of first order Taylor expansion. So one has to end up with something which is linear, but this is just plainly not the correct thing we have to observe. So yeah, this leaves us as a loss because, well, first we managed to improve our continuum description by including fluctuations in this linear way. But now we see that if we're interested in rare events, then the continuum description in form of the linearly corrected model doesn't do the trick anymore. Okay, so the question becomes, well, how can we incorporate construct a nonlinear model incorporating fluctuations, which at the same time shows this improved approximation order? So where the approximation order behaves better than n to the -1/2, and at the same time also displays the correct rare event behavior, which we need in order to understand effects like metastability, like tipping point behavior, which you would see in climate change and so on. So these are rare events, but they're still important events because they can interact with the nonlinear dynamics to significantly change the overall behavior of the system. Okay, and this is now the starting point of the nonlinear theory of, in this context of the nonlinear SPD theory, because we now set up an ansatz for this improved continuum limit. And yeah, I just throw it in. So ansatz looks like this. We look at the hydrodynamic, this first part looks like the hydrodynamic limit, right? So we have the diffusive equation with a nonlinear structure. And now we correct this again by adding fluctuations to the system of this precise form. Again, okay, it has to decay when n goes to infinity, so we have a small factor in front. It has this divergence structure because it has to satisfy that total mass is preserved. And now we have a decisive difference to before because we have actually the diffusion coefficients depending on the solution in a nonlinear way. Right, and also here it's not linearized in contrast to the linearly corrected model, but really the full nonlinear dynamics, and also here it's a nonlinear dynamics. And formally I can write this down, and this is sort of in the spirit of Langevin dynamics for SDEs. But it's, yeah, and the important point I want to make here is that this is, and I will argue for this, that this is the correct way of incorporating fluctuations into this SPDE. Of course, there are many ways. You could say, okay, I have like my hydrodynamic limit with this nonlinear diffusion equation, then there are fluctuations, so I just add some generic noise term, but then you wouldn't know anything about the specific structure of the noise term. And I'm arguing here that this should be the one that you should actually consider when you're interested in fluctuations coming from the microscopic system. Now, before going into arguing for this, let's look at one special case, which is the case of independent particles. So yeah, there's always a special case incorporated what I'm showing you. Then the nonlinear equation phi would just be linear. So this would just be the identity function. So we see that again, the deterministic dynamics would just be the heat equation, so mass diffusion. But the interesting point I want to make here is that even in that case, the SPD that we see is far from simple, because we still see the derivative of space-time white noise, so it will be very irregular in general. And then we also see that we have the derivative hitting a square root of the solution. So this is sort of reminiscent of what you see in Dawson-Watanabe SPDE, but in this conservative form that you have a derivative in front of the noise. And this does have a name. This is goes back, for example, to Gin Kawasaki, and there are many people yeah, working on this particular case. And here we motivate it in a more general form, where we even see nonlinear diffusion and then different diffusivity also in the noise. Right, so how to come up with this ansatz? Well, first of all, this has been around for a while. So because in physics, starting with the fluctuation dissipation relation was a physical principle, how fluctuations should relate to dissipation, which is precisely what we see here. We see fluctuating term and the dissipation term. And yeah, by this fluctuation dissipation relation, which is often used in the field of fluctuating hydrodynamics, this would precisely prescribe that the fluctuating model should have this form. Okay, this is now sort of a black box that I'm telling you that in non-equilibrium statistical mechanics, this doesn't come as a surprise, but is a generalization of the fluctuation dissipation relation. Now, maybe more appealing for mathematicians is that we can read off that this ansatz satisfies all the properties that we wanted to have. So first of all, it doesn't perform worse than the linearly corrected model in the sense that it has the correct mean behavior, and in the sense that when we write down the central limit fluctuations, so now we look at the stochastic Pde solution, we subtract the hydrodynamic limit, we blow up this error, then again we can see that we have a central limit theorem in the sense that there is a non-trivial limit, and this limit is again described by a linear SPDE which has the correct form, meaning that our solution rho n to the continuum object, so this is still the solution to a stochastic Pde, so it lives on a continuum of real numbers in between 0 and 1, and not on a discrete torus. It does specify the correct Gaussian fluctuations in the large n limit. Okay, so far this would also be true for the linearly corrected model, but now the point is that this nonlinear model, it also captures the correct large deviations. And right, so this we haven't seen yet, and I want to give you a very informal way of seeing that in principle it should be the correct thing. So right, so how to see the informal large deviation principle, where we just pretend that the contraction principle from large deviation theory works or is applicable here, which means that we pretend that the solution map, which I call now capital F, which maps the noise that we plug in, which is a rescaled space-time white noise, onto the solution to the SPDE, that this is a continuous map. Well, so we know that this is not true even in the setting of SDEs. We just pretend it is, which makes this an informal and to some extent incorrect argument. But it does give us the same, the correct guess for the rate function. So namely, the contraction principle tells us that the ray events or rate large deviation principle of the solution map, it should just be given as a variational form, taking the infimum over the rate function of the thing we have on the left-hand side, so the space-time white noise, and taking the infimum over level sets of the solution map F, which maps a control G, which used to be the noise, right? So now we place the noise by the function G onto the given fluctuation rho that we want to observe. The point is that the right-hand side in this equation, everything is identified, because this is the large deviation, or the rate function of space-time white noise, which is just known to be the L2 norm. So here is where the L2 norm pops up and why in the variational description of the rate function, we always saw like this infimum of the L2 norm. And then we take the infimum over all controls G, where G are chosen so that if you map it via the solution map to the nonlinear SPDE, you get rho. Okay, in other words, this means that rho should be a solution to this equation, which looks now precisely like the SPDE that we started off with, but replacing the rescaled noise by the control G itself. Okay, so, and this is also how you could come up with the SPDE just by reverse engineering this form of variational form in writing down the ray event, or the rate function. Right, so this is indicating that indeed we did the right thing, and this nonlinear stochastic PDE should describe the correct large deviation behavior. So now what's the caveat here? The problem starts on the very first line that I started with when I described this Langevin type ansatz, because, well, this is just not a well-posed stochastic PDE. In the sense that it has the derivative of space-time white noise. So this is what we call a supercritical stochastic Pde, which means that even if we zoom in and look on local scales of this equation, then it will always be dominated by this fluctuating term. So even on local scales, it doesn't look like a correction about the mean local linear model, which you would see in subcritical settings, and which is the starting point, or one of the fundamental principles in the theory of regularity structures, which would be the closest thing in form of looking at singular SPDEs. But this is not applicable here in a fundamental way, because this is a supercritical and not a subcritical situation. Right, so first of all, it's not clear how to deal with well-postedness, and then even if you were able to do to adapt like regularity structures, then there would be the question of the renormalization, because in singular SPDs you typically don't really solve this singular SPD, but you have to correct by subtracting renormalization constants or coefficients, which are sort of minus infinities, which would appear in this equation. And only if you subtract them, you get the non-trivial limit. And this is a problem because, well, if we subtract these kind of renormalization constants, it's absolutely unclear if they would appear in the corresponding resulting rate function. And this is something we don't want, because the rate function is fixed, right? We know how the rate function precisely looks like from the deterministic, from the discrete system. So there's no wiggle room there for renormalization. And yeah, and situations of quantum field theory, this kind of thing and effect has been discussed and has been observed that you have to be careful with renormalization when looking at rare events. So I'm pointing to this paper by Hira and Weber for more details on this. Now, the point is that, on the other hand, we're sort of overcomplifying things here, because we're looking at a space-time white noise, but we want to think of rho to be an approximative model of the discrete system. And in the discrete system, actually, there is a decorrelation length scale, which is not 0, as it would be for space-time white noise, but which has the box sizes, right? So in each box size, we have independent noises. Particles independently choose to jump and where to jump, but on the box, it's constant, right? This is just built into the discrete system. So actually, when we think of the zero-range process, there is a typical decorrelation length scale, which scales like 1 over n, which means that, in a sense, when we write down this continuum model, we are overcomplifying things by writing down their space-time white noise, but we should write down a stochastic process which decorrelates on length scales of order 1 over n. So there would still be something which looks like a modified or a smoother noise, which just approximates space-time white noise when n goes very large. Right, and this is now the specification of the ansatz that we suggest. So we suggest to study this as two-scale setting where we look at an ultraviolet cutoff of the noise. So we introduce a decorrelation length scale, which we call capital K. And then we show that if you do this, you can, first of all, make sense of the stochastic Pde. So this is now well-posed, which is a theory in itself, and it took a few years to develop, but this has been done. And then one can see that given the correct scaling behavior, so looking at situations where the noise amplitude is much smaller than the ultraviolet cutoff, specifying this here, then indeed this limiting, this continuum model, it does satisfy all the properties I was stating on the last slide, namely it shows the correct mean behavior, the correct central limit behavior, and this is the content of the papers that I'm presenting, it does provably show also the correct rare event behavior. Right, and this makes rigorous general link in between what is called macroscopic fluctuation theory. This is a general theory set up by these authors in non-equilibrium thermodynamics or statistical mechanics, two different way of writing down fluctuations in non-equilibrium, which is so-called fluctuating hydrodynamics, which goes back, for example, to Spohn and co-authors. And yeah, in between these physical theories, there's a link which precisely goes via a formal large deviation principle. And the works that I'm presenting make this informal link rigorous in the specific cases that we consider here. Right, so I'm looking at the time, I should stop. So maybe just to give you a very quick hint on what this now means mathematically, I just want to point out that although everything I said so far was closely linked to probability theory and concepts of fluctuations, when you prove a large deviation principle, actually everything becomes questions about non-stochastics or deterministic PDEs. So I just want to finish by pointing this out, that proving an LDP boils down to proving actually well-postness of nonlinear PDEs, which take this form. So now I specified the nonlinearity to have this power-like structure. So now we see a porous medium operator here, and we see a convective term, which is nonlinear. So even with m equal to 1, this is still the square root of rho, so this is something nonlinear, and which takes a control G, which is a
Ben, are you here?
yes.
Okay. Sorry, you were stuck. Maybe you repeat, maybe.
Oh, I was stopped. Oh, that's bad. Okay, so I don't know where I lost you, so maybe...
At the skeleton equation that it is nonlinear, even if m is 1, you had the square root of rho.
Okay, thank you. Thank you. So yeah, the point is, the main difficulty here is that G is very irregular. So it's just an L2 function, which comes from the point that just the rate function of spacetime white noise is given by the L2 norm. So there's nothing we can really do about this. We really have to solve it for this irregular G's. And they're much more irregular than what you would suspect to be able to deal with. So if you think back of the theory of Deterministic or Le Brilliance, which look at well, these diffusive Fokker-Planck equations with irregular coefficients, or also just transport equations, then you also need always need some regularity assumptions on G to make this well posed. And here we have much less, which makes this challenging. Okay, so the main problem becomes well-posedness or existence and uniqueness of solutions to this skeleton equation, and its stability, in the sense that we need stability with regard to the driving control G. When they converge weakly, we need strong convergence of the solutions. So once we have this, the proof of the large deviation principle is immediate by the weak convergence approach by Dupuy and co-authors. But the real difficulty boils down to a PDE problem to solve this guy. And this we do in the paper. This is the main chunk of work. So we introduce concepts of renormalized solutions, generalizing the works of Deterministic to this nonlinear settings that we have at hand. So we have to deal with the nonlinearity of the diffusion here. And we have to work with new and optimal regularity estimates that we get from entropy dissipation in order to control commutator errors as you would then expect them to appear in setting up a concept of renormalized solutions. Okay, but this is just an introduction to this whole work, so you're welcome to dive into the details of the papers, of course, and also there are some more details contained in these slides if you have a minute after the talk. So yeah, at this point I want to stop, so I'm just giving you the references. So I said there's a background of works behind this. Just the ones that I concentrated on in this talk is this one with Nicholas P. and Ben Fairman, and this one down here with Ben Fairman. In this one we treat the zero-range process, and in this one we give the full treatment of the symmetric simple exclusion process. All right, so yeah, thank you very much for your attention, and yeah, my apologies for taking a few minutes more than anticipated. Thanks.
Thank you very much for fascinating talk. It was very interesting. Are there any questions?
And Professor Ortega Pivonka has a question. He has permission to speak.
Hello?
Yes.
Excuse me?
Okay.
Yeah, sorry. Thank you very much for your talk. I just have a couple of kind of out of the box questions. First, if you have used, if you have done anything to try to incorporate fractional diffusion, I mean, yeah, anomalous diffusion and fractional derivatives in your model. And the second, this is a hard one, but I was wondering if you know anything about the applications of this kind of research, continuous time random walks, and financial mathematics.
So the quality was not so good in the second question. Could you repeat that one, please?
Yeah, no. If you have seen any applications of this this type of research in financial mathematics or other areas of industry.
Oh, okay. Mm-hmm. Okay, so I mean, as to the first question, for fractional behavior, then so in this setting, I would expect that you could construct something like this, but you would start with different microscopic systems. So you would start with a system which, in the hydrodynamic limit, converges to a fractional equation. So yeah, depending on where you want to see a fraction operator, so it could be you look at.
You allow me to interrupt?
Yes.
Sorry, just I think you can have anomalous diffusion if the waiting time for particles to jump in the lattice follows a specific type of distributions other than the Poisson process, for example. So you have to choose.
So,
I don't remember too much about this. I have.
Yeah, maybe the simplest way to construct something like this, it could be to let your particles not run by independent Brownian motions if you are looking at, for example, the Dean-Kawasaki equation, but let them run by Levy processes, then certainly the mean behavior would be a fractional Laplacian, which would be the generator of your process. And then, yes, you could study the fluctuations and try to set up fluctuation description of this hydrodynamic limit. So I think the principal question is the same as the one we investigated here. You have to be a bit careful at some points that the fluctuation dissipation relation can become more complicated if you start looking at more Poisson time jumps, because then you might run into the setting of what you would call a generalized gradient flow rather than a gradient flow. And then the setup for fluctuation dissipation relation is not so clear. So the noise actually might enter in a more nonlinear fashion than what we are used to when we write down stochastic PDEs. And then it would not be so clear how to write down the fluctuation continuum analog. As to applications for finance, my answer would be negative. I haven't seen that, but I also haven't investigated it. So it might actually be an interesting comment, I think. You might think that there should be relations to things like mean field games when you look at large systems which interact, which do have individual noise, and then you look at the mean behavior in the mean field limit, and you could also study the fluctuations around this mean behavior, and it's conceivable that there you would see or could come up with fluctuations corrections which might take a related form, because, well, you do see the mean behavior given by a non-local Fokker-Planck equation in mean field games. So when you look at fluctuations, yeah, it would be conceivable that they would have just the Fokker-Planck part would have a similar form, and then it would be coupled to the Hammond-Jacobi equation. So yeah, that might be possible, but yeah, this is just my immediate association with the question.
Okay,
Thank
so
you very much.
yeah, I have one question about the equation. Maybe if you can show the slide with the equation where Brownian space-time Brownian motion is cut off with k. Yes. 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 That's it. So this is a Stratonovich integral, as I understand. Yes. So in the limit, if you take full space-time Brownian motion, then Stratonovich correction is infinite.
Yes, so yes, very good question. So the answer in this case is that when you write down the Stratonovich correction, then this also sees the amplitude, which goes like 1 over n in the correction term. And this explains also why there's a certain scaling that becomes critical at some point. So this is chosen so that actually in the limit, the correction term would go away. So the choice of stochastic integration becomes irrelevant for the large deviations that we see due to the scaling. Yes. But it's a very good question and point you're making. So the scaling is relevant, and we see a sort of critical scaling to what I'm saying, which would be of the type 1 over n behaving like 1 over k. So once they start behaving on the same scale, then you might see the Ito or Stratonovich corrections appearing.
Thank you. Are there any other questions?
Yes, Ben, I have a question just to this slide. So how does the ultraviolet cutoff look like, the rho k? Which kind of cutoff function we are using?
Well, I mean, I would be thinking about just like a Galerkin projection, right? So you expand your white noise in terms of a basis, and then you cut off after the number of noises. How important the specific cutoff is, I would have to think. So I would think that if you mollify it, then it should also work. Certainly the microscopic picture works, and then so I think it's not like bound to that. So it's instructive to think of Galerkin projections, but you could think of mollifying with a kernel which converges to a Dirac, and then rescaling this kernel like 1 over k.
Okay, thank you.
Okay, so perhaps we should stop now, but everyone is invited to coffee break, so we can connect on Zoom in a few minutes. Everyone should have received an email with the link to the coffee break, and then we can continue the discussion about mathematics and about other topics which we want to discuss. So thank you, and see you in a few minutes. I will close the meeting.
Yeah. Thank you, everybody.